Let us begin with something simple. Something almost childlike in its innocence. How big is the universe? You might expect a number. Scientists love numbers. They will tell you that the observable universe is approximately 93 billion light-years in diameter. They will say it with confidence, with precision. They will draw diagrams and show you simulations with billions of swirling galaxies, stretching to the edge of the visible cosmos. But that number, 93 billion light-years, is not the size of the universe. It is the size of the universe that we can observe. There is a difference. And that difference is everything. The universe is not 93 billion light-years across. The universe could be infinite. It could be 1 trillion times larger than what we see. It could be so enormous that our observable bubble, with its 2 trillion galaxies and its billions of years of cosmic history, is so small by comparison that it would not even register as a single atom on the surface of something far, far grander. And we have absolutely no way of knowing. This is not a gap in our technology. It is not a problem we will solve with a better telescope or a faster rocket. This is a fundamental, hard mathematical boundary written into the laws of nature itself. It is called the cosmic horizon, and it is the most profound limit ever discovered in the history of human knowledge. So how did we find this wall, and why can we never cross it? To understand that, we need to go back, far back, to a moment 13, 8 billion years ago when everything, all of space, all of time, all of matter and energy, erupted from a single point smaller than an atom. We need to go back to the beginning. The Big Bang was not an explosion in space. This is the first thing most people get wrong. And it is an important mistake to correct, because if you picture the Big Bang as a giant fireball, expanding outward into empty space, like a bomb going off in a dark room, then everything you think you know about the universe is built on a false foundation. The Big Bang was an expansion of space itself. There was no room into which the universe expanded. Space did not exist before it. Time did not exist before it. The Big Bang was the moment space and time came into being, and then stretched rapidly in all directions, carrying matter and energy along with it. Now, here is where it gets strange. In the very first fraction of a second after the Big Bang, we are talking about a time so short it makes a nanosecond look like an eternity. The universe underwent a period of expansion so violent, so rapid, so incomprehensibly fast, that it expanded faster than the speed of light. Wait, can anything move faster than light? No, objects cannot move through space faster than light, but space itself has no such speed limit. Space can expand at any rate it chooses, and in that first explosive moment it did. It expanded so fast that regions of the universe that were once side by side were suddenly separated by distances so vast that light, even traveling for 8 billion years, has not yet had time to cross the gap. This is the wall. The cosmic horizon exists because the universe is old enough that light from certain regions has had time to reach us, and young enough that light from other regions has not. Every point in the universe has its own horizon, its own observable bubble. And those bubbles do not overlap. They cannot communicate. They are, for all practical and physical purposes, separate islands in an ocean with no shores. But here is what makes this truly remarkable. Light from the very edge of our observable universe, the light we see today as the cosmic microwave background, that faint glow of ancient radiation that fills the entire sky, that light left its source when the universe was only 380 years old. It has been traveling toward us for 13.8 billion years. And in all that time, it has crossed a distance of 46 billion light-years. Not 13.8 billion, because space itself has been expanding during the journey, stretching that distance like marks on a balloon being inflated. That ancient light is our last signal, our last photograph. Everything beyond it is dark, not because there is nothing there, but because there has not been enough time for any information from beyond that boundary to reach us. And here is the most haunting implication of all. The universe is still expanding. Right now, as you listen to these words, the cosmic horizon is not standing still. It is moving. And not toward us, it is moving away from us. Galaxies that are currently just barely visible to our most powerful telescopes will, over the coming billions of years, recede beyond the horizon, carried away by the expansion of space, their light stretched into invisibility, their existence forever erased from our observable sky. The observable universe is not growing. It is slowly, quietly, irreversibly shrinking. Now we must ask a more unsettling question. If the observable universe is only a fraction of the total universe, how large is the total universe really? The honest answer is, we do not know, but we have theories, and those theories are staggering. One of the most widely accepted frameworks in modern cosmology is called inflation, the idea that the universe underwent that period of exponential expansion in its first moments. Inflation theory, developed by physicist Alan Guth in 1980, was not invented to explain the size of the universe. It was invented to solve a very specific set of mathematical puzzles about why the universe looks the way it does, why it is so smooth, so uniform, so flat in its geometry. But inflation, as a side effect, makes a prediction so extreme that most physicists find it deeply uncomfortable. If inflation happened, and the evidence strongly suggests it did, then the universe it produced is almost certainly vastly larger than what we can observe. Not 10 times larger. Not 1,000 times larger. The numbers that fall out of inflationary models suggest the total universe could be at minimum 10 to the power of 23 times larger than our observable bubble. Some models suggest it is infinitely large, literally, infinite, with no edge, no center, no boundary, just space stretching on forever in all directions. And if the universe is infinite, truly, mathematically infinite, then something extraordinary follows. Something that sounds like science fiction but is a legitimate, peer-reviewed implication of mainstream cosmology. In an infinite universe, everything that can happen does happen. Every possible configuration of matter, every possible arrangement of atoms, not only occurs once, but occurs an infinite number of times, which means that somewhere, infinitely far beyond our horizon, there is another version of this planet, another version of this solar system, another version of you, listening to these exact words, in a room that is identical to the one you are in right now, and not just one version, an infinite number of versions. This is not philosophy. This is mathematics. This is what happens when you take infinity seriously. But let us go even deeper. There is another theory that lives at the edge of modern physics. A theory so bold, so strange, and yet so mathematically compelling, that many of the greatest minds in science take it seriously. It is called eternal inflation. And it changes everything. In eternal inflation, the period of rapid expansion that gave birth to our universe did not simply stop after the Big Bang. It is still happening, right now, in regions of space so far beyond our horizon that no signal from them can ever reach us. Space is still inflating, expanding at that furious superluminal rate, and as it does, it creates new universes, pocket universes, bubbles of space that slow down from inflation, collapse into a hot, dense state, and then expand into their own cosmos. Our universe is one of those bubbles. The Big Bang was not the beginning of everything. It was the beginning of us. The moment our particular bubble of space cooled down from inflation and began its slower expansion, the moment our specific set of physical laws crystallized into existence, because here is the profound part. In eternal inflation, different bubble universes do not necessarily share the same physical laws. The constants of nature, the speed of light, the strength of gravity, the mass of the electron, these may not be universal, they may be local, properties of our specific bubble. Other bubbles may have different constants, different forces, different dimensions, different rules entirely. Some of those universes might not form stars. Some might not allow atoms. Some might collapse back on themselves within fractions of a second. And some, a small rare fraction, might produce conditions hospitable to complexity, to chemistry, to life. We may live in a universe fine-tuned for life not because someone designed it that way, but because we could only exist in a universe capable of producing us. This idea, the anthropic principle, is not a comfortable one. It strips the universe of its apparent specialness. It says that our cosmos, with all its extraordinary precisely calibrated constants that allow stars and planets and chemistry and consciousness to exist, may simply be one lucky ticket in an incomprehensibly large cosmic lottery. And yet, there is a question that even this framework cannot answer. Why is there something rather than nothing? We have arrived at the edge of what science can say, not the edge of our courage or the edge of our imagination, the edge of what the scientific method, with all its magnificent tools of observation, measurement, and mathematical reasoning, can actually reach. Because here is the fundamental problem with everything beyond our cosmic horizon. It is, by definition, unobservable. In science, we test ideas by making predictions and comparing them to observations. But the multiverse, that vast sea of other bubble universes, that infinite landscape of cosmic possibilities, produces no observations we can verify. No signal from another universe has ever reached us. No experiment can probe beyond the horizon. The entire framework of eternal inflation and the multiverse is, in the strictest sense, untestable. This makes some scientists deeply uncomfortable. There are physicists, brilliant, careful, serious physicists, who believe the multiverse is not science at all, who argue that a theory which cannot be tested is no different from mythology, that we have simply dressed up our ignorance in mathematical clothing and called it an explanation. And they are not wrong to worry, because throughout the history of science, there have been moments when the apparent complexity of the universe tempted thinkers into grand, unfalsifiable explanations. Medieval astronomers invented elaborate systems of celestial spheres to explain the motions of planets. They were beautiful, they were mathematically sophisticated, and they were wrong. Are we doing the same thing now? Are we building cathedrals of mathematics to house a mystery that simply lies beyond our ability to understand? There is a deeper philosophical wound here, one that cuts to the heart of what it means to be a conscious creature in this particular universe, at this particular moment in cosmic history. We may live in a universe that is fundamentally unknowable. Not because we are not smart enough, not because our instruments are not precise enough, but because the universe has a built-in veil, a horizon woven into the fabric of spacetime itself, beyond which no knowledge can ever travel. We are, in the most profound sense, cosmically alone in our ignorance. And that is not a small thing. Centuries ago, human beings looked up at the night sky and believed they were at the center of everything. Then Copernicus moved us off center. Then astronomers moved our solar system to the outer arm of an ordinary galaxy. Then cosmologists showed us that our galaxy is one of 2 trillion. And now we are told that those 2 trillion galaxies, that entire luminous cathedral of creation that took 13.8 billion years to build, may be nothing, an invisible speck, a quantum fluctuation in the vast, dark, silent sea of everything that actually exists. How does a mind hold that? How does a conscious being, made of atoms, living for perhaps 80 years on a small, rocky planet orbiting an ordinary star, look into that abyss and maintain any sense of meaning? Richard Feynman once said that the most beautiful thing we can do with science is to live in the question. Not to demand an answer, not to retreat into comfortable certainty, but to stand at the edge of what we know, look honestly into the darkness, and feel, really feel, the weight of what we do not understand. The cosmic horizon is not a failure from science. It is its greatest achievement, because in all of human history, no generation before ours has ever known that such a horizon exists. No ancient philosopher, no medieval scholar, no early modern scientist had any idea that we lived inside a bubble of light and time, with a hard boundary built into the laws of nature. We are the first humans to know the shape of our own ignorance. And that knowledge, strange and humbling and terrifying as it is a form of wisdom. The universe is not required to be comprehensible to us. The fact that it is comprehensible at all, that the same laws which govern the cooling of your morning coffee also govern the expansion of the cosmos, that the mathematics invented by human minds to solve abstract puzzles turns out to describe the behavior of reality with extraordinary precision, is itself one of the deepest mysteries there is. We do not know what lies beyond the last wall of light. We do not know if the universe is finite or infinite. We do not know if we are alone in our observable bubble, or if an infinite sea of other realities surrounds us in every direction. We do not know if the constants of nature are fixed or merely local. We do not know if our Big Bang was the first, the only, or one of an eternal cascade of beginnings. What we know is this: we are here, we are conscious, we are small, we are brief, and we looked up. In all the possible universes that might exist, in all the bubble realities, and cosmic landscapes and infinite configurations of matter and energy, something happened in this one. Carbon atoms organized themselves into nervous systems. Nervous systems asked questions. And one of those questions was so large, so deep, so beautifully unanswerable, that it has echoed through every civilization and every century of human thought. What is out there? We built instruments to find out. We mapped the sky. We traced the microwave glow of the ancient universe. We calculated the geometry of space-time. We pushed our mathematics to its limits. And at the end of all that effort, all that ingenuity, all that centuries-long collective reaching toward understanding, we found a wall made not of stone or darkness, but of time and light. And beyond that wall, everything or nothing, or something we do not yet have the language to describe. The journey to the edge of the observable universe does not end with an answer, it ends with a deeper question. And perhaps that is exactly as it should be.